let's dig in to some examples. Each one is going to involve Newton's second law for translation and second law for rotation. First things first, we're going to check out these situations, starting with a falling yo-yo. We have a yo-yo whose mass m equals 0.05 kilograms with an outer radius r equals 0.04 meters. That's the green circle in the animation. And the inner radius of 0.01 meters, which is the red circle. The yo-yo's rotational inertia is 1/2 mr squared. What acceleration will the yo-yo have as it falls and unrolls? First, we're going to make an extended body diagram. Use the diagram to make a net force equation. Does this sound familiar? You start with a force diagram, and then you create your own equation using Newton's second law, stuff that makes it go minus stuff holds it back, equals mass times acceleration. Yes, it does sound familiar because we've done it so many times. Solve the equations for the unknown. So the extended body diagram shows us all of the forces acting. The only forces acting are the weight, acting from the center of mass, and the tension, which is acting from this inner circle. The net force equation, stuff that makes it go minus stuff that holds it back. Gravity is making it go on the way down, and tension is holding it back, equals mass times acceleration. The net torque equation, only tension acting at radius r produces torque. So the net torque equation is r times ft equals I alpha. R is the distance away from the axis of rotation. Because this is a circular disk, then the axis of rotation is acting exactly at the center point of that circle. The tension force is acting upwards, which is perpendicular to this distance here. Gravity is acting exactly at the axis of rotation, so we know that to not be generating any torque. Set that equal to I times alpha, which is the rotational equivalent to mass times acceleration. Rearrange for whatever it is that we're looking for. So starting with the torque equation, we have I equals 1/2 mr squared. We can plug that in. We also know that A equals alpha times r, so alpha equals A over r. Note that we can use radius r because that's the radius the string is going to be connected to. So r times F becomes I times alpha. R is 0.01 from the very first step in the problem, and then solving for tension, we can divide out that 0.01. And we get tension equals 0.4 times A, whatever A is. Then we're going to plug that into our net force equation to figure out whatever the acceleration is. So this idea of going back and forth between our translational equation and our rotational equation, this happens, especially on FRQs. So remember that we have that bridge between the two right here with R times F. That is our bridge for the torque. We've also used one of our bridge equations to get our alpha. That's why that chart that we did way back in 7.1 is so important. Plugging in to the net force equation, we get 1.11 meters per second squared.